These are Air Force ballistic missiles on an assembly line. 7 years of intensive research and development stand behind them. A nationwide industrial complex has been devoted to their production. The goal is a reliable deterrent force, one that will convince a potential enemy that we can deal him a mortal blow should he attack us. Time is the key word, and to make time work for us, the Air Force Systems Command has developed management procedures as advanced as space-age technology itself. While the missile is being produced and refined, so is its supporting equipment, so are its operational sites. The name for this method is concurrency, all steps together, a jump forward in time. It even includes training crews before the missiles themselves have proved to be operationally ready, so that all elements of a missile force will be integrated on a pre-planned operational date, the earliest date possible. Because of concurrency, we now have squadrons of Thors, intermediate-range ballistic missiles, deployed and ready in the United Kingdom. And here at home, we base the long-range missiles, the ICBMs, like Atlas. Atlas was first operationally deployed on gantry-type pads at Vandenberg Air Force Base, California. Today, Atlases are deployed in horizontal readiness launchers. As early as September 9th, 1959, Strategic Air Command crews were capable of launching a missile from this configuration. Again, concurrency had paid dividends. But the quest for missile reliability has not been an easy one. The book of knowledge for missiles and space is just being written. Out of the first 75 Atlas flight tests from the Atlantic Missile Range, 50 were tallied as successful. 25 were not. Of the 25, 18 were considered partial successes. 7 were failures. If the reason for failure is not always clear, the reason for flight testing is. A missile flight test is more than just an example of repeatability. Each flight has something new on board, some new test objective to advance the state of the art, to move ahead. When Atlas was 5 years old, in tests for accuracy, it had placed re-entry vehicles more than 5,000 miles downrange, within 2 miles of the target. As a long-distance runner, Atlas was in a class by itself, continually outdoing its own track record for distances in excess of 9,000 miles, with re-entry vehicles impacting on target. Telemetry and photography have documented Atlas's growth. Here you see some of the films. After boosting a re-entry vehicle into the proper trajectory, the main body of an Atlas falls away, and now the cameras record multicolored stars and the Earth hundreds of miles below. These pictures from another Atlas flight were taken at an altitude of 700 miles, where man has yet to venture. And here is re-entry, a nose cone streaking through the Earth's dense atmosphere. While the missile airframe burns behind it, the re-entry vehicle successfully takes its beating and is subsequently hauled from the sea by the crew of a recovery ship. And all the while, our deterrent force continues to grow. Across the countryside, squadrons of Atlas missiles become activated. At Warren Air Force Base, near Cheyenne, Wyoming. At Offutt Air Force Base, near Omaha, Nebraska. And at Fairchild Air Force Base, near Spokane, Washington. Soon, more advanced Atlases will be deployed at bases outside cities like Abilene and Altus, Topeka and Lincoln, Plattsburgh, Salina, and Roswell. Some Atlases will be in hardened, underground, horizontal launchers. Some will be in inverted silos that can withstand the effects of enemy attack and still be able to retaliate. Atlas borrowed the silo idea from our other home-based large liquid-propelled ICBM, two-stage Titan. From its inception, Titan was designed to be deployed underground, then raised on an elevator, fueled and fired. The first flight of a Titan missile took place in February of 1959. A year later, in 1960, a Titan missile flew its first two-stage flight test. By shedding its first stage at altitude, Titan gains a weight advantage over Atlas, allowing Titan to hurl a heavier payload farther, thus bringing additional power to our deterrent force. Here you see separation of stage 1 and ignition of stage 2. During the first half of 1961, progress was recorded on a second-generation Titan. Engine tests were begun at contractor facilities. These engines developed more thrust than their Titan predecessors, and they used storable propellants that appreciably shorten countdown time. Where Titan 1 was dependent on land-based radio guidance, Titan 2 would carry an all-inertial system, virtually jam-proof. On June 23, 1961, the first flight test of a Titan 2 inertial guidance system took place at the Atlantic Missile Range. A modified Titan 1 was used, and the guidance package performed successfully. Meanwhile, concurrent with the flight test program, Titan Strategic Missile Squadron facilities were under construction. Missile silos, launch control centers, equipment terminals, guidance antennas and crew quarters, all underground, all being rushed to completion to be ready when the missiles are ready and the crews are ready. At Vandenberg Air Force Base, prototype silo facilities are used to verify designs and develop procedures for missile squadrons still under construction. On May 3, 1961, this Titan facility at Vandenberg received its test by fire. This was the world's first free flight of an ICBM from a protective in-silo environment. Its complete success verified not only this silo's design, but $100 million of Titan base construction already underway. Our third home-based ICBM, Minuteman, has 3 stages, 3 solid propellant rocket engines. The first flight test of a Minuteman missile took place on February 1st, 1961. It was the most successful first launch ever experienced by an Air Force missile. All 3 stages were sent aloft functional. All 3 worked. Here, through the eyes of a roti camera, you see separation of the first stage and ignition of stage 2. When stage 2 flight terminated, separation occurred again, along with stage 3 ignition, and the dummied warhead was placed in a ballistic trajectory destined to impact some 4,600 miles downrange. Operationally, Minuteman will be launched directly from an underground silo. Proof that it could survive this critical environment was achieved in 1960 through a series of tethered launches at Edwards Air Force Base in the Mojave Desert. 18 tests were planned, but the first 8 were so successful that the remaining 10 were canceled at a savings of millions of dollars. The first wing of Minuteman missiles is now under construction at Malmstrom Air Force Base, Montana. And thanks in part to lessons learned in Thor, Atlas, and Titan base activation, by mid-1961, construction of Minuteman Malmstrom facilities was 56 days ahead of schedule. Advances in Air Force ballistic missile programs have not only strengthened our deterrent posture, they have also formed the basis for our achievements in space. Thor has become a workhorse. As early as October 1959, Thor put a space probe dubbed Pioneer 1 71,300 miles from Earth. But 1960 was the year when space achievements began to come one right after another. Able Project, Pioneer 5, was the front runner. On March 11th, leaving its Thor booster far behind, Pioneer 5 set out for a planet-like orbit around the sun. For 22.5 million miles, it sent back messages to Earth, establishing new world records for communication from deep space. On April 1st, a Tyros weather satellite was launched for NASA and immediately began to observe, record, and transmit pictorial weather data from altitudes up to 450 miles. "22,000 photographs in all. Less than 2 weeks later, Transit, the navigational satellite, was Thor boosted into orbit for the U.S. Navy. Then, somewhere out in space, Transit's Able Star second stage was shut off and restarted upon command from the ground. Another space first. Agena vehicles, produced on an assembly line basis, became the backbone for the best-known Air Force space program, the Discoverer series. Agena's payload can be varied. In space, the vehicle can be reoriented, directed, and controlled. It can communicate and restart. By mid-1961, 14 Agena vehicles had successfully achieved orbit, and their various sensors had gathered voluminous data that answered many questions pertaining to space environment. A prime objective in the Discoverer program was the recovery of a capsule ejected from the orbiting satellite. On August 18, 1960, the first successful air snatch of a capsule ejected from a Discoverer satellite was made by the crew of an Air Force C-119. The capsule was from Discoverer 14 and had been ejected after the Discoverer had orbited the Earth 17 times. Soon, other Discoverer catches were made after 31 and 48 orbital passes. Sea recovery by the Air Force Pararescue Team was used to retrieve the capsule from Discoverer 25. It was the first time that air rescue teams participated in an actual Discoverer recovery, further insurance for a successful mission. Mounted on top of a modified Atlas, an Agena vehicle was used in support of Midas, a missile alarm and detection system now under development that will be able to spot ICBM launches anywhere in the world. Since September of 1959, the Air Force has been responsible for providing and launching boosters for the space programs of all our military services and for the National Aeronautics and Space Administration. To date, the payloads we have put into space have depended upon modified IRBM and ICBM boosters. One exception is this Blue Scout test system. Its solid propellant engines, or stages, can be stacked in different combinations, allowing Blue Scout to boost payloads of from 25 to 1,000 pounds to altitudes of from 200 to 50,000 miles. Economical, versatile, and reliable, Blue Scout will be used to support a number of our inquiries into outer space. The orbital voyage of a man in a Mercury capsule will soon take place, boosted by an Atlas missile. An advanced booster will place Dinosaur, a manned glider, into orbit, and Dinosaur will introduce precise pinpoint controlled recovery of a manned vehicle. Work has already been started on the propulsion systems of the future. Solid segmented rocket engines, capable of developing 1/2 million pounds of thrust, systems that can support multi-ton payloads, and clustered liquid propellant engines, developing a thrust of 6 million pounds, are now on research and development test stands being perfected. Payloads destined for the moon and beyond are becoming realities. Yesterday's and today's highlights have been spectacular. Through them, we have gained a foundation of knowledge. A higher order of space exploration is next, as we enter the second generation of the space age.